Hello, my name is Matthew Feiner, and here is the final report update for my MEMS 5001 project. My project is to optimize an NBA regular season schedule, given the constraints that each team play 41 home games and 41 away games, each team plays in-conference and out-of-conference teams a certain number of times, and no team can play 2 games in one day. This gives a total schedule of 1,230 games. The schedule is constrained by the rules set by the NBA, arena availability, national TV schedule, and other smaller constraints. I decided that the objective function I wanted to use was to minimize back-to-back games to improve overall player conditions and minimize the standard deviation between each team's number of back-to-back games to improve the overall schedule fairness. Back-to-back games are when a team plays a game on 2 consecutive nights, and back-to-backs are often cited as one of the most straining aspects of a schedule on player health. They also contribute to competitive imbalance, where teams on back ends of back-to-backs only win about 43.6% of the time. I used the following model to solve this problem. I created a 30 by 30 by 168 size array of design variables. This represents 30 potential home games, 30 potential home teams, 30 potential away teams, and 168 possible days the game can be played. Each design variable is represented by X with subscripts I, J, and T, where I is the home team, J is the away team, and T is the day of the game. The binary variable equals 1 if that potential game takes place, and 0 if it does not. After deliberating on which optimization method to use to solve this problem, I landed on simulated annealing due to the nonlinear nature of my objective and the constraints of the problem. I solved this problem by importing an already accepted NBA schedule and finding neighboring solutions that still satisfied all of the constraints. This was done by switching 2 games on different dates and then checking to see that no team plays 2 games on a single day. The constraints set by the NBA rules, such as that teams play a certain amount of games at home and the amount of times that teams play each opponent, will be maintained with this switch. I ran 10,000 iterations of this switch to find a better schedule. Like standard simulated annealing processes, the algorithm accepted a solution if it was better for an iteration, and also had a probability of accepting a worse solution to minimize the chances of falling into local minima. The objective function was a weighted function that accounted for both the total number of back-to-back games as well as the standard deviation between each team's back-to-back totals to account for the schedule fairness. Weights were adjusted to determine the best combination. Here are the results of one of my runs. The table on the left shows each team's original back-to-back total compared to the total from the optimized schedule. Each team's total decreased by varying amounts. The total number of back-to-backs from the original schedule was 398, while the total number was 317 in the optimized schedule. Similarly, the standard deviation decreased from 0.944 in the original schedule to 0.6261 in the optimized one. Here's a plot of the weighted scores against the iteration number. A lower score is more desirable, and the scores decreased as expected. The plot is not quite linear as the slope generally flattens out over each iteration. Although this solution doesn't take into account many desired objective criteria, such as travel distance or TV ratings, this method could potentially be used to account for those factors. More testing could lead to improved weights for the different objectives, and adjusting the probability criteria in the simulated annealing process could minimize the risk of falling into local minima.